Good evening, Professor Ristu. Good evening, Professor Ristu, sir.
Good evening. Actually, it's an early morning for me, but
Okay, good morning.
almost the same time, 8:30, something like that.
Okay, sir. Naresh sir has joined. Hello, sir. Naresh
Yes.
sir.
Hello.
Yes, sir.
Hello. Morning, Professor Resto. Hello. Am I audible?
Yes, sir.
Okay. Morning, Professor Resto.
Good morning,
Hello.
Dr. Norris.
Morning. How are you doing?
Great. I'm all awake
You looked,
because you guys are probably a little tired by now.
yeah, true. It's heavily raining. Actually, evening 5 o'clock it started, heavily raining. So just now we were able to transport ourselves from home to office to home. That's the issue. You look different. You have changed.
Different. Well, one thing is I have to start wearing glasses. I have 10, 11 hours of Zoom every day now, and I need glasses. I haven't had a haircut for 6 months. That's another thing.
Oh, okay. Okay. How is the COVID situation there? Is it okay?
Well, yeah, here most recently it's the wildfires that have been giving us trouble. So I really would like to have some of your rain here. Clear the air. Can't go outside because of COVID, can't go outside because of smoke. So it's not really great.
Okay.
On the other hand,
Okay.
if you are wearing a mask, you kill two birds with one stone. Anyway.
Okay. Okay. Thanks for joining us. Shweta, can you read the biodata of Professor Risto? Hello?
Okay, sir. Okay, sir. So I take the privilege to introduce our today's speaker, Professor Risto Michelin. Risto Michelin is a professor of computer science at the University of Texas at Austin and a fellow at Sentinel Technologies. He received an MS in engineering from the Helsinki University of Technology, Finland in the year 1986 and a PhD in computer science from UCLA in 1990. His recent research focuses on methods and applications of neuroevaluation, as well as neural network models of natural language processing and self-organization of the visual cortex. He is an author of over 370 articles in these research areas. He is on the board of governors of the International Neural Network Society, an action editor of Cognitive Systems Research, and an associate editor of IEEE Transactions on Computational Intelligence and AI in Games. We are very privileged to have you, sir. You can start your session. Thanks for accepting our invitation.
Yeah, and I'd much rather be there in person. And as a matter of fact, I was there a couple of years ago and gave a number of talks in Hyderabad, and that was really, really fun trip. Was hoping to do it again, but as things happen, can't always manage. But this is hopefully going to be interesting, and it's related to the problem why I can't be there. First of all, do you see my screen? Evolutionary Surrogate-Assisted Prescription.
Yes, sir.
Okay, great. I'm sharing just the desktop because I'm going to be dragging a demo into it. So yeah, this is now work that we've done recently in the last year or so, although we've been building up to it for quite a while. And it is a mechanism for making decisions, better decisions. And we are also applied it to the COVID-19 pandemic mitigation and containment. And this is my team at Cognizant who's been working on it. Olivier is a main architect, and Santiago, Elliot, and Shen produced some of the technology as well as Hormuz, and Babak is the leader of the entire group at Cognizant, the Evolutionary AI group, who's also overseeing this project. So Very tight team. Everybody contributed quite a bit, and I'm happy to be able to talk to you about it. So Santiago and Elliot are also students of mine at the University of Texas, Austin. So here's the big picture. How do we make good decisions? That's a question we'd like to understand. Today, organizations have a lot of data. All organizations, hospitals, supermarkets, educational institutions, they know what their patients doing, how their customers are behaving, and what the students are learning and how. And it's possible to build predictive models based on that data. In these situations, this is what you expect will happen. But those models do not actually make decisions. They help humans maybe to make decisions, but they don't tell you what you should do. And that's a different learning problem. So let's get that clear right off the bat, that prediction is different from decision making. Prediction is part of it, but the actual suggestions of how you should change your behavior is a different learning problem. And it's a hard one. We don't know usually what the optimal decisions are, like what treatment should the patient receive, or how you should organize the shelf so you increase sales, or how do you organize the training material so your students learn better. And part of it is also that the domain is not completely observable. You don't know everything about your patients, customers, or students. You know some things, but there are other factors that come to play, and you'll never have them all. And these factors interact in a nonlinear fashion. So there may be a rainy day, and that might totally shut down your shoppers if it's really raining hard. And you don't even know that. So those are some of the challenges that make optimal decision making hard, learning to make optimal decisions hard. There are direct methods, such as linear programming and various gradient descent based methods that people have tried to use, but they don't really apply to these kinds of decisions for these reasons. LP is linear, obviously, and only a few variables can be taken into account, and you can't use gradients unless you have something to propagate them from. So the solution is to learn by searching, trying out different strategies, and then improving them, changing them, and trying them out again, and this way searching for good decision strategies. It is costly, of course, to do that in the real world. You can't really experiment with patients, for instance. You could experiment with your customers, but if you make wrong decisions, it's also costly. In some cases, there are simulators available in robotics, perhaps, if you try to come up with robotic control. But even in robotics, we know that it's difficult to transfer from simulator to a real physical system. So this is something that makes it difficult, and that's where we've been thinking about it for quite a while, how we could do this right. And here's a general framework of the suggestion of the approach that we are proposing. And it is to use surrogate models and do surrogate optimization. So we actually have two models in this approach. One of them is a surrogate of the world. And you can train that using your supervised methods if you've collected such data from the real world. So if you have collected situations, contexts where decisions are made, and you record the decisions, and then you record the outcomes of how well these actions worked in these contexts. These might be particular patients, the treatments, and how well they recovered. Or they might be product characteristics, and then you make marketing decisions, and then you see how much money you make. All kinds of applications can be mapped to this triangle. And the first point is the prediction, that when you have such triples, you can use them to train a predictor. And then you can evaluate any suggestion for actions in any context, how well the outcomes would be. And now the idea is that if you have such a model, you can use it in lieu of the real world. And when you are searching for these good prescriptions, these models or strategies or policies that map your context to the actions, you can test how well these prescriptive models work, not by deploying the decisions in the real world, by asking the predictor, how well does the predictor think these decisions would work. And that's a huge improvement because we no longer have the cost of evaluating something in the real world. We just evaluated another model that we trained with historical data that already exists. So that's the general idea for surrogate optimization. Now, this is still difficult. The search space for those decision strategies is likely to be nonlinear and deceptive, something like this instead of something like that. A very large and very high dimensional, and there are multiple objectives. I mean, you want to cure the patient, but you also have limits in how much it can cost. So almost, or same with marketing or anything, you usually have at least two objectives. One of them is the performance and the other one is a cost. And you have to find your, your optimal trade-offs there. And there are certainly methods that have been applied to these kinds of tasks, like Bayesian primary optimization or Kriging, trying to do this black box optimization by asking a surrogate, or reinforcement learning. And it's difficult for those methods as well. And that's because the space looks like this, and it's because it's large, high-dimensional, multi-objective. These techniques don't lend themselves well to this kind of scale-up. And there's quite a bit of work on surrogate-assisted evolutionary computation, and that's the starting point, that maybe that can be extended to this surrogate-assisted decision-making as well. But the difference is that here we need to evolve a strategy, a mapping from context to actions, any context to actions, not just finding a single optimal point, like usually in surrogate optimization or black box optimization is the goal. You have an unknown function and you try to find its maximum or minimum point. But here we actually want to have discover an entire strategy, a mapping, maybe a neural network or something. And that's the idea. We evolve neural networks to represent that strategy. So evolution is the search method, but neural network actually implements it. So that's what evolutionary surrogate-assisted prescription is, or ESP. And that's the idea that we combine a neural network surrogate with a neural network strategy in this triangle. And the surrogate is trained with the data, historical data, and the strategy is evolved against the surrogate. And you know, there are variations. You can have other kinds of predictive models. They could be random forest or so. You know, your prescriptors could be rule sets. It still fits the general model. And in a couple of examples, I show you these two are neural networks, but they could be something else as well and still be part of the same approach. And it's interesting that this did not come from a vacuum, even though I said we've been working on it for a year. We developed applications that eventually came together with this idea of putting them together. CyberAg here in the middle was one of those. This was the application where we evolved growth recipes for agriculture, in particular vertical farming, containers that were computer controlled. Everything that goes into this space, in this to these plants, is computer controlled. Temperature, light, nutrients, water. We can come up with any kind of recipe we want. And the question is, well, what is a good recipe? And turns out nobody knows. Farmers know about their patch of land, but if you could control everything, what would you do? And this is where we used evolutionary search. We searched for those growth recipes, and we evaluated each one of them against a surrogate. A model that we had built by collecting data on a good, large, broad set of recipes, how well they actually grew basil, how tasty it was, how large was the plant. So we had a model, a predictive model, a surrogate, and then we evolved those recipes directly. There was no prescriptor. It was really just evolving individual recipes. There was no mapping. But it was an idea that, hey, we need this surrogate, we can build it, and then we can search for good recipes. And it worked great. We discovered, for instance, that basil doesn't need to sleep. Keep the lights on and it will thrive. It was a big surprise to biologists, but evolution discovered it. And this, on the right, there's another application which focused on this part here. we evolved neural networks to map a user who comes to a website to a customized web page that they then see in order to maximize the chance that the user will click on that action button. In this case, it's find my program, find more about these medical schools, for instance. Or it could be buy something, a buy button, or sign up, or something like that. That's conversion optimization. And we're using evolution to maximize conversions. But the interesting bit was that we evolved neural networks to map what we knew about the user who came to the site, like their location, time of day of week, their operating system, internet carrier, things like that. We mapped that description to a customized version of the page. And that worked really well. Now the evaluation, there was no surrogate in this case because we just showed those images or showed those pages to users directly. We didn't need a surrogate, but it told us, showed us that we can evolve such prescriptors. So now ESP is really putting CyberAg and Ascend together into this triangle, and then it applies to a lot of different domains. Okay, so what I want to talk about next is to go a little bit deeper into what ESP is, what these components are, and analyze some interesting interactions between the components that we didn't even expect would happen, that make it work much better than we actually thought. There's more than, it's more than the sum of its parts. And then I'll show a couple of examples in game playing, comparing to some reinforcement learning techniques, for instance, and then an application on the COVID-19 prediction and prescription. So let's start with the prescriptor. That's the meat, that's the new piece, that's the exciting addition to what state of the art is. So the goal is to find a policy, a decision policy or strategy that optimizes the outcomes. And that's expressed in this neural network, most likely, or something else like a rule set, that we call the prescriptor model. And it maps the context to actions. And again, the optimal actions are not known. We don't know how to respond to a current situation, for instance, but we have ways of evaluating them, and that's important. We have to build a predictive model to do that. Now, this is easy. In some sense, it's easy. It's standard machine learning. And that's the job here, is to take the context and the action, the pair of these, and then predict what the outcomes are. And now we can evaluate any prescriptor candidate. We can throw various contexts to the candidate, observe its actions, and put those pairs as input to the predictor and get the outcomes. And over such a sampling, we get an average performance of the strategy. And it can be multi-objective. We can train the neural network to predict multiple dimensions, cost and performance. And like I said, this could be a neural net, but it could be something else as well. And in some special cases, you could even use a simulator from first principles, physics simulator. And in some sense, something like Ascend, where we have a real world do it, plays the role too. So those are like degenerate cases where ESP is a generalization of a lot of different implementations. Now, then let's think about putting this together and making an implementation based on that triangle. Well, the triangle turns into a square. So in principle, we could learn it in one step, that we collect the data first. Then we use the data to build the predictor, train it with backprop or something. It might be a deep learning network, for instance. And once we have the predictor, then we use evolution to give us the prescriptor. And then we find the best possible prescriptor, and that's then applied into the real world. And we're done. I mean, that may be it, that we just go through this once. But in most practical applications, the world changes. We prescribe something and we observe the outcomes, and that becomes additional data for us to train. And we can go back and retrain the predictor with more data, retrain the prescriptor with better predictor, and then iterate. This could be something that happens once a year, once a month, or something like that. But the idea here is that it's relatively static. The prescriptor gets applied for quite a while, and we occasionally do an update. And that makes sense. Our world is like that. If you think of website design, for instance, people's tastes change, and there's seasons that change, and we'd have to keep changing those sites. People just get bored with them too. So it is a process that allows this kind of continual adaptation. Now, we have also a different kind of application of ESP, and that's when it's really in a tight loop with the world, that we are making multiple decisions continuously and then observing outcomes perhaps continuously, or maybe in the end. And that's, for instance, thinking of game playing. When we start, we don't have a data set. And we generate a prescriptor just randomly. It's a neural network with random weights. It makes random decisions, random actions. Well, in a game playing world, you could do it. You can play the game and see what the outcomes are. And in that sense, you start by creating a random prescriptor so that you can collect your data. In some domains like games, indeed, you can do it. You could even do it in some real world domains, but you would have to have some existing prescriptor that's not already bad as a starting point, because you would otherwise incur very high cost. But the idea is that you start here, and the first job is to generate a lot of data. And then you train a predictor, and you evolve a prescriptor, and you then loop and generate more data. And this can be very tight, this loop. You can have the predictor being continually trained, and the prescriptor continually evolved. So this loop is happening pretty much at every sample that you do. And this is fascinating. When we did this, we didn't know it, but it turns out that there's a fascinating synergy that emerges. While the predictor and the prescriptor are learning at the same time, they actually regularize each other, and you get better performance than you might get if you just try to do it one step at a time, like one phase at a time. Okay, so that's great. That's a general setup. Now, in order to apply it to the real world, we need a couple of more things. If you want to deploy a decision-making system with some customer, somebody or policymaker or somebody who actually uses it, they are more likely to use it if the system gives them also measures of confidence, or measures its uncertainty, estimates uncertainty on those decisions. So we have, for instance, a system that gives you recommendations, and then the predictor gives you estimates of how well they're going to turn out, how much money you're going to make, how much the cost is going to be, what's the chance of the patient recovering, how much it's going to cost. We have to be able to tell what the confidence intervals are around it. Otherwise, the person making the decision has a hard time accepting it. Turns out we can do it. And this was a separate research project we had to do in order to make it more likely to people who actually make decisions would use the system. And the idea here is quite interesting. You already trained a neural network to make decisions, for instance. And now you can see how accurate it is. You know where its errors are. You have, this is a neural network that makes the predictions. So it predicts, given its context and the decisions, it predicts what the outcomes are. And because we have a training set for prediction, we can see what errors it makes. And those errors are residuals, and we can train another model to predict them. And we use Gaussian process because Gaussian process gives you confidence intervals already. And here's another kind of interesting surprise, that the Gaussian process learns the world differently. I mean, we are a neural net that does as well as can be done with the data. It makes some errors. Why would another model be able to predict the errors? How is there anything to learn when you trained it as well as you can? Well, it turns out there is, because Gaussian process is a different kind of learning system, and it learns a little bit different regularities. And in this process, the Gaussian models learns to predict the errors, learns the distribution of errors. And this was a surprise. We can actually use the mean of that distribution to correct the outputs of the neural net and do better. So by training another model to predict the errors, we can actually correct some of those errors and get better, more accurate predictions. So this is a whole another paper. Just wanted to mention it because that's an integral part of ESP. If we want to deploy something, we want to know how trustworthy the decisions are. And Rio, this mechanism is going to give it to you. Okay, there's another dimension of trustworthiness for this decision making. Again, if you want to deploy it in the real world, and that is a Scratchpad. So when your prescriptor makes these recommendations for actions, it is very useful to let the user modify them by hand. The user is an expert in the field. Most likely the user has some ideas and he or she is looking at the prescriptor output and going like, well, that looks a little odd to me. I wonder if I changed it this way, what would the outcome be? And then the decision maker can deploy the predictor to evaluate that change and see how well it might have worked, what the predictor thinks, how good those modifications might be. And in that sense, there's a whole Scratchpad, and the user can either find something better by hand if they have some extra knowledge or expertise, or else search and fail to improve the prescriptions, and then convince themselves thus that the prescriptions are as good as they can be. In either case, there's more trust in the decisions, and the decision maker is more likely to deploy them. Now, even if the changes were made and the decision maker deploys something that wasn't actual prescription, we still get new training data from that. These decisions in these contexts result in these outcomes, and we can continually take that into account and improve the prescriptor and anticipate what the decision maker would be likely to do, how the decision maker would change the actions. So those two elements are practical in making deployment possible. Now let's look at a little bit what happens in this process of learning the predictor and prescriptor at the same time. And here's the first domain, which is a really simple one and just put together for visualization. We'll look at games and the COVID later. So here's a very simple domain. The context or the state, the context is a number, single number between -1 and -10 and 10. And the action is similarly just a single number from -1 to 10, -10 to 10. And here, the color here in the background in this area shows you the best policy. So if you are at 0, if that's your context, then output a 0. That's the maximum value. If you're at -5, output -2. That's your maximum value. So that's what you see here. The value is encoded in this color scale. That's the ground truth. That's your optimal policy. And we just assume that. We just set it up by hand in order to visualize how the predictors and prescriptors learn. And here is a snapshot from an animation of learning. The background here is not the ground truth, it's actually the predictor. So this is how the predictor would reward different actions at different states. So now if you are at, say, -5, it will give you 0 as the best action. If you are at 10, it would give you 10 as the best action. So this predictor hasn't really learned this ground truth, because the best action at 10 is actually -3. It thinks that it's 10. But the color coding, same color coding as for ground truth, applies to the background here, and it tells you what the predictor thinks the ground truth is. So it's incompletely learned at this point. And then there's these couple of fun plots here. The dashed blue line actually tells you what the true optimum prescriptor is. The optimal actions are along this sine wave. And we can see it here against the ground truth, but here we just plot it so you don't forget what it looks like. And then we have the current prescriptor, at this stage of learning, this is what our prescriptor will tell you to do, this orange line. And then the white line is a prescriptor that would give you maximally good feedback from the current predictor. So it follows the bright areas of the background, and it goes all the way up here. So that's what the current predictor would reward the highest. It wants you to develop a prescriptor like this, even though we know by our oracle, we know that this is the correct one, and this is currently what the prescriptor actually is. So you can already see kind of the bottom line, a sneak peek, that the prescriptor isn't fooled by inaccurate predictors as much. Its prescriptions are still better than what the predictor would have you do. Okay, let's see how that comes about. Here we have a little animation that shows all this learning happening at once. So we see the predictor in the background changes, and then we see the prescriptor in the orange line, it also changes. And at the same time, we see the white dotted line, which describes what the predictor wants you to do. So watch, you see that the predictor, the white line, is all over the place. And the orange line is pretty much learning way ahead of the white line. Eventually, they both focus and concentrate on the actual sine wave, but it takes a lot longer for the dotted white line to do it. So the predictor does not have to be nearly optimal for the prescriptor to learn an accurate prescription. And this was a big surprise for us. We didn't think this would happen. We were really worried that inaccurate predictors would just throw away the learning, throw off the prescriptor learning, and exactly the opposite was true. Inaccurate predictors are okay, and for some reason, the prescriptors that learn are surprisingly good, better than any individual predictor would have you believe. Why would that happen? Why would that be the case? And if I could see you, I might be asking a question and you might want to answer, but I don't know if this is intended to be two-way. And it takes a little bit of thinking, actually. It may not be obvious. But the reason why this works this way, why the prescriptors are regularized, is that each prescriptor is evaluated against many different predictors. The predictors change all the time, and the prescriptors are evolved against many of those. So the predictors serve as an ensemble. And the ensemble, on average, has a better idea what the ground truth is than any individual predictor. And therefore, the prescriptors learn to regularize, even though your predictors are all over the place. So that's pretty clever. It wasn't clever because we didn't decide it. It was just a lucky break, perhaps. Well, maybe I take that back. We had that in mind all along. Just trust me. But at least we take credit for it. So it was a really nice surprise that this kind of effect came out. All right. Now, here's again a couple of frames from that animation, and here are some comparisons. If you try to directly evolve the decision maker, the prescriptor, without any predictors, without a surrogate, it's a lot harder, turns out. This is after 100 episodes. This is after 1,000 episodes. We are nowhere near the ground truth. And this is all, after 100 episodes with the surrogate, we're already doing really well, much better than any of these. And this is a pretty much state-of-the-art reinforcement learning approach, PPO, using the same number of episodes to learn the prescriptor. And by 100, it's pretty much a flat line. By 1,000, it starts to curve a little bit. And it eventually gets there, but it takes a lot longer than this ESP, Surrogate-Assisted Evolution. So that's a nice comparison. It tells us why this is working and demonstrates why that it's working better than other methods. We can also apply it to other tasks. Here's well, actually, this is more of a quantitative comparison on the same domain. Here's the learning curve for ESP, the learning curve for PPO, and for direct evolution from previous slide. You can see that there's a lot more variance in these other methods. ESP converges really quickly to the optimum, and PPO eventually may get there, but is slow and is unreliable. There's a lot more variance. This is showing the regret, the cost of all these episodes when you're making mistakes. And you see that it goes down really quickly with ESP. There's more regret with PPO and direct evolution. So ESP is also lower cost and safer. It doesn't make quite as many mistakes at all. Now here's another domain. This is one of the standard reinforcement learning benchmarks. It's the card poll domain from OpenAI Gym collection. And here we have both PPO and DQN implementation, standard reinforcement learning methods, deep reinforcement learning methods. And here we see a similar effect. The ESP has very quickly converges and then is very reliable. There's very little variance. There's much more variance in DQN and also PPO even in the end. I mean, you have to have this variance in order to explore and in order to learn. And also direct evolution has a lot of variance. And here's the regret. The regret goes down very quickly and much faster and is much less than in the other methods. And by the way, here I must say, if you have questions, I have the chat window right there. I mean, you could just, you have such a small number of people, I guess. I don't know how many is behind each camera, but if you want to just open the mic and ask, that's fine. But you could also type them out into the chat, and I have it right there, so I should be able to notice it and respond to any questions. All right, so similar result here. Learns faster, has better solutions, lower variance, lower regret. So that's a pretty good starting point. But now let's try to apply it to something more interesting. And this was something we did have in mind, another type of regularization. That maybe it's not just that we have multiple predictors that serve as an ensemble, but maybe there's also an effect that the predictors, as they learn, they first learn a simple approximation of the domain and then gradually more veridical, more complex approximations of it. And if they do, they would actually regularize. They would help the system to learn simple parts of it, the task first, and then gradually be more accurate. And that actually happens. And we can see it even in something as complex as the game playing. This is the Flappy Bird game. It's a fun little game. There's this bird whose task is to fly through these pipes. They call the pipes, they're gates. And you have to go through the openings. And they are sometimes high up, sometimes low down. They come from the right side. Actually, let me just play the movie. It's a little easier to see. And your job is to flap. And that flapping moves the bird up. If you don't flap, it sinks down. And this way you try to fly through the pipes and not crash into them. And there's a 2-minute track and you try to get through that. All right, so that's the task. Now here on the left, we are showing what the task looks like to the prescriptor. What does the predictor think the task is as it learns? And indeed it learns simplifications of the task at first. And then it starts to predict the more complex cases of it. And here we are showing it as a video, the predictor's view of the world. Like you remember, the background was a sine wave, but the predictor's view was kind of, all over the place. Well, here we have the same thing. It's just shown in terms of where the pipes are and what the movement is like. And it turns out that in this more complex task, actually you learn simple predictions first. So the first thing that happens, oops, wrong movie. First thing that happens is that it tries to present the challenge of finding the opening. Go to the opening. And that's all it's doing. Once the bird gets through the opening, it tries to get it to fly through it and then start to pay attention to the next opening, like right there. Slow it down so it can figure out how to get to the next one. And the next one comes very soon, very quickly, and it's very close by. And that makes it easy. And then once the bird gets through those, it starts to present you multiple pipes at certain distance, but they all in the same place. So it's very easy to fly through them. And then in the end, the predictor has become good enough that now the pipes, the openings are in different locations. And it actually has to go through and make the flaps right. And I'm not sure how nicely this video comes through. It seems to be choppy even on my screen a little bit. But if you go to that website, you can see this video, both of them and some others too, and you can see it better. But you know, my verbal description tells you what you need to know about it. It's a fun visualization of this regularization effect that the surrogate does. And because of that effect, we get a tremendously much faster learning than we could without it. All right. Now let's go to COVID-19, an actual real-world application for ESP that a lot of people have in their mind today, obviously, the whole world. So here, the goal is to cope with COVID-19 better than we are doing now. And it is outlining a new role for AI in this challenge. There are lots and lots of predictive models, like this one here, actually. It shows you that here's the time series of cases, the daily cases over time. And here we are today. What is the future going to look like? How many cases are we going to have until the end of the year, for instance, in this case? That's a predictive model. And you can predict it based on the time series of cases, but you can predict it better if you take into account what kind of restrictions there were, non-pharmaceutical interventions, like where the schools closed, where the workplace is open, was public transportation functioning, was there stay at home order, masks were compulsory. All these are non-pharmaceutical interventions that try to change people's behavior in order to make this curve go down. And that's a time series as well. And we have to take that into account in order to predict the future. Well, we don't know what those NPIs might be in the future, but we can predict what would happen if the current NPIs were held. Or what would happen if we changed the NPIs? How would the curve look like at that point in the future? So that's then still a prediction. But what's new about ESP approaches, we bring in a whole another level. We're not just optimizing and making more accurate predictions, but we are coming up with policies for the NPIs. We're actually trying to figure out what to do. Not just what will happen, but what should we do about it? What kind of NPI should be established at this point so that we get the cases to go down, and at the same time, don't have to close the whole economy, don't have to lock down the world. People could still possibly continue working, but if we had certain other kinds of interventions. What are those interventions so that we minimize the cases and minimize their cost at the same time? Two objectives. So the first step is to build a good predictor that takes into account the cases as well as the NPIs. And turns out there are data sets out there, in particular Oxford, Government Response Tracker. These guys put together a data set that they started early this year, and they're still collecting it. They're still updating it, at least until the end of the year or so. And they have about 100 people that are reading government announcements and press and collecting this data and lining up the different NPIs at different countries so that they become part of the same metric so we can learn from them. And that means that there's now at least 11 kinds that we are taking into account of these NPIs, and each with the different levels of stringency, how costly they are, and how strong they are. Now, standard compartmental models that have been in existence since about 100 years, they based on epidemiological assumptions of susceptible and infected and recovered people and their interactions. You have to set those by hand, and it's very hard to do. So what we did instead is to build the predictor based on data. We actually have 2 time series, and we train them with the time series on all the different countries, 187, I think, so that we can learn to predict, even without understanding the underlying dynamics of the disease. And the advantage is that we actually don't have to have assumptions about what people do. We just observe the data, and all the nonlinear interactions are already there, expressed in the data. So there's promise that if we have enough data and it's accurate enough, we can do better than these compartmental models, because they only can do as well as their creator, how good they were in setting the parameters and setting those compartments. This requires a lot of human work based on differential equations. It's technology from 100 years ago. Differential equations then, large data sets now. Okay, that's the predictor. The design looks like this. We have one sequence processor based on LSTMs for the cases, and another one for the NPIs, the sequence of NPIs. And then we predict what will happen the next day, and then we have a mechanism for rolling it out over many, many days. So the prediction becomes input for the next day, and then we might observe NPIs changing, so that input sequence also changes. So this takes about 28 days of the past as an input to make one prediction, and then we loop. And here we have then also Rio, as I pointed out, the uncertainty metric. I'll tell you how confident we are. This is like the 25 and 75th percentile, the quartiles around the prediction. So that's the predictor. How well does it work? Pretty well, actually. Here are some cases of actual true data in green, and we made the prediction here, and as you see, the prediction, the orange, follows it quite well. This curve is without any NPIs. This is taking into account the NPIs that are currently in place at that point. We're doing pretty well. This is in Italy, pretty early in the pandemic, while they're still trying to get in control. This is in Germany, about the same time. I think it was May or something. And here again, a different kind of a curve, but still the predictions are pretty accurate compared with real data. And we've done it in a number of different countries, pretty much all of them, and measured the confidence, and this setup does work. It's pretty accurate. And it's accurate enough to start making prescriptions. So here we have the setup for the prescriptor. It sees the same sequence, and then it recommends actions. Here we are showing 8 of them. We've since expanded to 11. Schools, workplaces, public events, gatherings, public transport, stay at home, restrictions on internal movement, and international travel. We also have testing policies, contact tracing, and public information campaigns like masks. That's also now part of it. And in the future, we might even include vaccination policies or treatment options. But right now, that's the data that Oxford has put together, and that's what we use. And this is indeed multi-objective. You want to minimize future cases as well as minimize the stringency. And we evolve these neural networks and then evaluate them with the predictor, as I already said. Now, because it's multi-objective, we get a Pareto front. And here's a visualization of that front. These are all, each dot is a neural network, something that we have evolved. This is a population of neural networks evolving over time. And some of these individual neural networks are really good at minimizing NPIs. They pretty much just open up the whole economy. Sorry, they are in here. Let's see. So this is the NPI cost. So the minimum cost is at the bottom. So these individual neural networks open up the whole economy. But as you see in this x-axis, they actually incur a high cost in terms of daily cases. And we have others that minimize the cases. The case numbers, daily case numbers are very low. But as you see, their NPI cost, the stringency of the NPIs is much higher. So we're probably looking for something around here where that minimize both the cost and cases simultaneously. And actually, this continuum, this Pareto front, is what we offer in the demo for you to choose so you can see what alternatives you have. And now I want to pull in the demo. And this is where it is. It lives in this website, evolution.ml. This is actually the research group website, but if you go to decision making, underneath that you have the NPI. And this is the demo interface. You can go to different countries in the world. There's 187 of them, I think. We don't have everything included. There had to be at least, I think, 10 deaths. So some of them are smaller countries, like, I don't know, Fiji or something, didn't have, Taiwan, I think, did not have enough. But we also have states in the US, Texas, for instance. And I think we are coming up with whatever they are, states in Brazil and Germany and India, possibly. They're not here right yet. And you can click on a country, and then you can select some options like show forecast for the current NPIs, show forecast where everything is maxed out or everything is lifted, and so on. So we click on India, and we get the prediction for India, and here it is. This is the historical data for India. India is one of those countries where things have been really still growing, even though there's a little blip here that seems to be hopeful, optimistic. And here we check the current NPIs. So the current restrictions, if they are kept constant, the cases will indeed keep going down. That's the prediction of the current model based on all the data we have around the world and their NPIs. And then we have the Pareto front in here as a slider or selector. And if we select something here, which is on the stringent side, we want to minimize cases more than we minimize the stringencies. So we picked this one from the Pareto front. It actually shows you that if we strengthen the restrictions, we can bring the number of cases down significantly faster than they would go down now. And here we actually see below that prediction plot, we see a prescription plot. So this is the history of the NPIs, of the restrictions over time. There are the different dimensions, schools, workplaces, gatherings, and so on the right, including now public information testing and contact tracing. And then the color coding here indicates how strong they were over time. And there are still some restrictions, at least Oxford, in Oxford coding. It says schools are still restricted. There's some mild restrictions on workplaces, and lots of public information happening, and so on. And then this is the current prescription. The prescriptor that was more on the stringent side, it actually would have more stringent restrictions on workplaces, stay at home, and testing, for instance. And if those were implemented, the prediction is that cases would go down significantly faster. And we can go and pick different prescriptions here. We can go pretty far to the right, and you can see that the predictions start to climb. So if you go all the way here, open up the economy more than it currently is opened, you see a lot of these restrictions are lifted. There's only a couple of them left. Lots of public information still, some on public events, workplaces always come up. It's the most important by far. And the prescriptions favor it by default more than the others, as well as schools. Now, in order to combine all of these into one metric of how stringent it is, we just simply add up all the stringencies of all dimensions equally. Now, that may or may not be what you want. In current economy, probably opening up workplaces is more important. So we should perhaps give it a higher weight. Give it 10 times the weight of, say, public transport or something else. They kind of go together, but we could start getting, with such constraints, such weights, we would get policies that try to keep the workplaces open and then make other restrictions in order to control the pandemic. But here it is. I mean, this is now currently equally summed up, and that's why workplaces come up as the most important one. And indeed it is. At work, people come together often indoors, and they are in close proximity with each other for 8 hours a day. That's how COVID transmits. That's the primary mode. So whatever we do at workplaces has the highest effect. That's at least something that the system has learned. Schools are a bit like that. At schools, apparently kids don't get sick as easily, and they also can be outside, and schools have been closed also for the summer. So it's become, in the Northern Hemisphere with most countries. So it's become less important for the model for the time being. It was more important when it started in March and April, when schools were open and they were a cesspool. And chances are, now that schools are back and a lot of schools are opening and in-person instruction is starting, we believe this is going to be more important in the next few months. And the model will learn it as the data comes in, because the data comes in almost every day. We retrain these models almost every day and update them, and we see different kinds of behaviors. We have already seen since May quite a bit of different behaviors come up. Right, so this was a very much more lenient one, and you see that eventually the cases will go down, but there's a chance, good chance, that it gets worse before it gets better. Now, if you go further to the right, we get some alarming predictions. These cases climb up quite a bit, dwarfing what we have today. And if we don't do anything, well, let's go all the way. If we don't do anything, we're looking at 15 million cases per day. Well, I'm not sure if that can be really accurate. It's so extreme that the herd immunity would probably develop within a few weeks or months if we don't do anything. But that's just showing that you cannot be complacent. Something needs to be done, otherwise the COVID will get out of hand. So that's fascinating. We can move along this axis and find different solutions to the pandemic, how to contain and how to mitigate. And you can pick the ones that you can stomach, that you can live with. And one extension we are working on is to give these different weights so that the decision maker could also say, no matter what, I need to keep my workplaces open. Give me the best alternatives. And then it would. And that's what you do. I mean, the decision maker then picks the desired trade-off. And that's how you use it. You move here and find the one that you can live with. And then the AI here finds the best prescriptions, the least cost to achieve least cases. And these are different for different countries. And different countries have had different profiles. We could go to, let me see, say New Zealand, a very different profile. And there's not a whole lot to do in New Zealand. The only thing that the system can kind of predict, actually we don't even have the confidence intervals anymore because there's too few cases to really calculate. The only thing that the model knows is that if you don't do anything, if you're not vigilant, there's always a chance that the pandemic will get out of hand again. So that's about the only thing. But the pandemic is, at this point, almost non-existent in New Zealand. So there's not a whole lot not to predict there. Actually, let's turn that off. We don't see anything if we just assume that there's no restrictions. So there was a peak and it went away. There was a little peak. They got it under control again. China is like that too. I think it's under control there and has been for a long time. There was a big peak and not much happening. US is a mess. And one reason is that there's just no uniformity in you. Looks like I clicked Missouri instead of the country. So we have to zoom in a little bit, I think. So in the US, we have the whole country and the states, and the US itself is obviously an average, a combination of everything. So this is a little difficult to make predictions and difficult to quantify the NPIs because they are so different all over. But we certainly see an interesting historical pattern. Some people call this phase being naive and this phase being stupid because most countries at this point went all the way down and the US started climbing. Now there's been quite a bit of progress, but this is a very disturbing trend. It looks like we are starting a third wave. This is now due to schools and universities opening. It's a new population, a new challenge, how to manage that. And we can go to individual states and see that their profiles are actually different. They are not the same as the whole country because those phases happened at different times in different places. So Texas missed the first wave because it was mostly New York, Boston. And now it had a second one. And this is where UT opened, University of Texas, where I am. That's where we opened and we started seeing everybody getting sick. It was ridiculous. Students came on campus. We gave them all the instructions to wear a mask, social distance, no parties, and they just flat out ignored all of that. Well, on campus they would have to behave, but off campus nobody can control them. Young kids, they think they're invincible. But the sad thing about COVID is that even though they may be, then they infect others, and then there's dire consequences when they go back home. Everybody's very concerned about Thanksgiving in particular, when all these kids go back home, see all the relatives, including their grandparents and so on. There's nothing good that can come out. Well, there are certain good things, of course, but there are some bad things that can come out of that as well. So looking at the curve now, it's not nice. You can go here, do a little zoom in of what's happening. There's sometimes serious fluctuation, but we have a pretty clear trend exactly when schools open. But we can control it. It's just a matter of doing the right thing. And that is being a big challenge, to get people to actually listen to science. We have the tools, and I'm showing you one of those that allows you to pretty convincingly get at least useful input to the decision makers. Whether they listen is a different thing. There are all kinds of constraints. And this is all new too. It's never been possible before to make such plots. We had 1918 pandemic. We had something in the 50s and 60s. And it wasn't possible. It was much more local. People didn't travel. And people didn't know what was happening. And we didn't have this kind of data. Now we do. And it's kind of a travesty that we have the tools, not only to see what's happening, but also make it better, do something about it, and we are not. So hopefully this demo will at least help people over time understand what's possible and start talking about it. So the next pandemic, when it comes, we will be better prepared. And believe me, there will be a next pandemic. That's even Bill Gates says that we are entering the era of pandemics. The world is quite connected now, but we can actually handle it if we do the right thing. Okay, I think that's enough for the demo. A couple of more points, and then we can open up for questions. I already talked about schools and workplaces. This was earlier in the pandemic. This is Italy, I think, in May, June. Schools were in session, and there was a very strong recommendation from the model to close them. Here is another interesting result. This was in US at the time. There's only so much that the prescriptions can do because we have coded them ahead of time. They cannot recommend things that are not coded. But one thing they could do is this alternation. So keep workplaces open, then close them, then open, then close, then open, and similar things in schools. And this is exactly what's being implemented now, at least here. The schools are open a little bit, then it's distance, then open a little bit, then it's distance. So this alternation was a creative solution that evolution found. We can also go back in time and see what could have happened. And this is important for the next pandemic. It's not very useful now, but we can, for instance, go to UK and we can see what would have happened if they had not shut down or locked down the country. The cases would have gone up like this. They did lock it down, and they got it under control at the time. But here's an interesting other prescription. If it had been implemented early enough, while people were still like in denial, if they had actually closed just the schools and put some restrictions in workplaces, the pandemic would never have gotten a foothold that it did. So this is a really interesting demo of the value of these tools and believing them. We can handle the pandemic without economic cost if we do it right. And here's another interesting result. In Italy, early in the pandemic, of course, it was difficult. Nobody really knew what was happening. They did instantiate a bunch of restrictions, actual full lockdown eventually. And they should have done better with those NPIs. That's what our system tells us. It's in here, whereas the actual cases were quite a bit higher. And this is really interesting because it suggests that Italy was behaving differently from the countries for which we had data at the time. Notice this is in March and April. So we had data for China and South Korea and other places where the lockdowns were more effective. In Italy, they were not quite the same. So there are cultural differences, there are demographic differences, and those would need to be taken into account to improve the NPIs and improve the predictions. All right, last point. So we believe that using this approach, we can apply it to many different aspects of decision making, in business, in education, in healthcare, and everywhere in society. There are these situations where we have historical data and we can intervene in order to achieve what we want. It's a question of what we want. If the decision makers can agree whether they want to optimize productivity or cost or environmental impact or equality between people, then they should let AI figure out the policies that need to be instantiated to achieve them, to achieve different trade-offs between them. So they have to pick the trade-offs, and then AI will figure out how to get there. And that's remarkable and brave, because it means that we can finally make a society what we want it to be. If we just agree what it is, we have an unbiased way of achieving it, based on AI, based on data, so that things like graft and personal agendas and pork doesn't get in the way. So there's a tremendous promise. When I first proposed it, it was, I think, an EvoStar 2019, and got a lot of pushback, but the point was that I didn't really have an example, but now I do. This is the example. COVID-19, it's very clear how this could work in COVID-19, in other pandemics, in other disaster responses, and by extension, society in general. So it's no longer possible to just ignore it. But clearly there are huge challenges in getting people to agree. But it would be wonderful if we could, because then we could do better. And in the future, it would be irresponsible to try to implement policies and come up with them by humans, because the AI could do it better. All right, to conclude, ESP, Evolutionary Surrogate-Assisted Prescription, utilizes the surrogate modeling and then evolutionary discovery to do well in decision making. And we get something that's efficient, reliable, and low cost and safe. And it also has this fascinating property of implicit automatic regularization when we are learning predictor and prescriptor at the same time. So it is a demonstration of how data actually, how powerful it can be, and how we are in a new era where data is king. It is no longer unreasonable effectiveness of mathematics as it was in 100 years ago when these compartmental models were developed. It's unreasonable effectiveness of data, like Peter Norvig likes to say, of Google. And we can use it to forecast, we can use it to make recommendations. We do have to be cognizant of the fact that in order to deploy, there needs to be measures of trustworthiness. and make sure that we are not biased and so on. So there's certainly challenges like that. We could replace some of the neural net with rules and rule sets that we evolve, so we can explain why things are happening. So that's still work that needs to be done. But in that sense, we could create decision-making, have creative decision-making in all aspects of life and society. So that's my conclusion. And if you're interested, go to the site and you can see more videos, and you have the interactive COVID demo there as well to play with. And I think we have a few minutes for questions, at least on the schedule. I don't know if anybody is still awake. It's kind of late here, but I'd be happy to answer questions.
I request participants to post your queries, if any, in the chat box.
A very interesting talk, Professor Risto. COVID-19 has given a new challenge. And then you could combine the prescriptor and predictive models. Really interesting work. I have one question that, these models are as good as the data, right? So how, this reliability on this data, the model, would we rely on that, right? So data itself is not reliable, then how good is the model? How much we can rely on that?
Yeah, that's a very good question. And we were very concerned about that in the beginning, and we still have debates about it with Oxford, actually. Just yesterday, we were talking about that again. Should we use death rates? Should we use positivity rates in testing instead of cases that are diagnosed? And all of those have their own problems. And there are certainly countries that are totally fudging their numbers and are not reliable at all. And even in the US, there's concern now that they were taken away from hospitals and made government controlled. But it was a surprise that even with all these flaws and inaccuracies in the data, there was enough to learn from. And maybe it was a similar issue as we showed in the ensembling effect in the function approximation, that we did have many predictors that were developed, and all of them were inaccurate in different ways. So overall, we got something that was robust. And it was surprising how well it actually does work. So that's still part of the research, is to explain why that happened. But it was surprisingly reliable, knowing how crappy the data actually is. But the data is not also, it's not completely crappy. I mean, there are certainly people are trying to collect data that's correct and accurate, as accurate as it can be. And in some countries, it's better than the others. And now the system does learn that there are some differences between countries and data sets. And it apparently learns to compensate for it. So as long as the data is more consistent over time, it learns to interpret what it means. It learns to compensate for at least systematic errors. It's a little more difficult when things change over time, but again, everything changes over time here. So there's maybe a lag of a month or whatever it is, a couple of months, and then the system catches up. But there are certainly challenges, like in UK actually, with trying to really collect data well. They discovered that many cases were counted twice. And on one day, we had minus 30,000 cases, instead of whatever 10,000 they used to have, or 8,000. That kind of throws the wrench into the predictions. But over time, it smoothens out. And again, we are doing accurate predictions. So like the ensembling effect, this is something similar to that. And it was a bit of a surprise. But it came from being able to get data from 187 countries at once, all of them flawed in some different ways. You get some average patterns, and that's what you need. There are, when you're doing machine learning, of course you want to be accurate. But if you are too accurate, then you will start overfitting. So if we, for instance, have our NPIs that are very fine-grained, we are not coding, say, transportation as one number of stringency, but we are separating streetcars and trains and buses and bicycles and whatever. We go too fine-grained, then these policies start all looking different. And our data is starting to look different from different countries. We have to establish enough overlap so that we can get the power from, and predictive power from the overlap. And I think Oxford has struck a pretty nice balance on that. And it turned out that then it also worked in favor of cleaning the data, or at least mitigating the problems with the data. So yeah, it's a very important consideration. We have to make do with what we have, but it fortunately turned out to be better than we expected.
Thank you, Professor Risto. We have one question from Naushad Rahim. He says, do these results reach the concerned governments?
Yes, that is a very big issue. So we've been trying to do that now that we have the demo, and we've been talking with a lot of different branches of government, businesses, various ways of gaining attention to it. And there's hope. We do have some excitement in places that are still, that are scientifically minded and would like to do better. Now, we are working on actual initiative to pair up modelers and people who make prescriptions with sites who would like to implement them. And also going further into next year and perhaps apply the same technology to optimizing vaccination policies and treatment policies if we get good treatments. So this is work in progress. It's much harder than developing a good predictor, for sure. But it's not hopeless. There are people who listen, and we don't have to get it everywhere. If we get it to a couple of places, maybe Los Angeles or a city like that, large city, where people are willing to listen and work with it. San Francisco, maybe. No, they are close by, so we can work with them a little easier. We don't mind. I mean, it could be Kinshasa, it could be New Delhi, whatever, Hyderabad. But we have some ways of reaching them through people who are well connected. But so it's still work in progress, and I wish maybe in a week or so I can tell you more about it, because we are working on potentially unveiling an opportunity to collaborate. But it's at this point, I can't really talk about it in more detail. Yes, that's a huge issue. And we've reached a point where we really want to make it happen, and we can. But it takes different kinds of expertise. As academics, we can't do it. We have to recruit folks who have connections with government and health agencies and so on. And that's a little bit different. And we have made those connections. We're working on it. Yeah, there was another question actually in the chat. Let me see.
I think it's a message
from Gaurav Singh Bhatti. Sir, earlier I was wondering how ML can be used for prediction. Now, with your great insight of the way of using the available data, I am extremely astonished that even ML can suggest us actions that we can do to achieve required outcomes.
Yeah, I'm not sure what the question is, but it is exactly what I said earlier, that we were astonished too, that the data was good enough to make predictions and prescriptions like that are accurate. There's still scientific work that needs to be done to understand how good they really are, going back in time, cleaning up the data some more when the data has become now more reliable, and then understand why it is what it is. But I've given you the hunch that we have now, and I do believe that it is never clean, but there is an ensembling and regularization effect that actually works when you make predictions, when the data is at a coarse enough level. So it would be much more difficult to recommend that, buses have every other seat empty or something like that, because it's very specific. But at the level that we are dealing with now, I think it works. Yeah, I don't know if I answered the question, because I don't really see a question there.
Thank you, Professor Risto. We will be connecting with you if any question comes up with the participants. We'll mail you or connect with you.
Sure.
Thank you so much. I propose the vote of thanks. Professor Risto, thank you so much for taking out your time. I think it's a bit odd hours even for us and for you as well. and still accepting and coming online. Thank you once again. Possibly you may visit India next year if COVID issue is resolved and a vaccine comes out. Hopefully I will see you in Hyderabad. I think the volunteers of Hyderabad ESP chapter have put a lot of efforts. I thank them for their efforts, and even the participants have stayed back late. So thank you everyone. As a token of appreciation, we are sharing with you a certificate, Professor Risto, and I will mail you shortly. Sweta, can you share the screen, please?
Sir, give permission to share, sir. Make me co-host. Allow all panelists.
All panelists, sir?
Yes, sir.
Yeah.
Please accept a token of appreciation, sir.
Sure. Thank you. My pleasure.
Thank you for your
Thank you, Professor Risto. I will mail you the certificate. So please do come next year to India. I will send an invitation. We are coming up with a conference 2021, Emerging Techniques in Computational Intelligence. So recently we got the CIS TCS. So I will share with you the details. Hope to see you soon. Thank you. Thank you everyone for joining. Bye-bye.
Thank you. Have a good evening. Bye.
Participants, I will share you a form in WhatsApp group. Please fill that. Thank you.